There are a couple of general mitigations that can be performed to make the Pipework's response more robust against vibrations, and these include tightening up the support clearance, which is effectively equivalent to adding additional supports, therefore increasing the stiffness and natural frequency of the system. And typically, the energy of vibrations will reduce with higher frequencies. Thus, the system response is not as efficiently driven. Do be careful when tightening support clearances, as this also impacts the thermal stresses of the system and could cause overstresses if not properly evaluated. It should also be noted that if there is a tonal excitation from a discrete vibration source, then there is a possibility that the alteration of the system's stiffnesses will cause the new natural frequency to become coincident with the excitation frequency, causing resonance of the pipework structure with this discrete vibration source. Another general mitigation measure is to avoid metal-on-metal contact. This simply reduces the risk of fretting. We can, instead of using metal-on-metal contact, use a wear-resistant layer of material between surfaces, if contact is necessary, such as with a pipe support. To mitigate against the source of AIV, we can do some of the following. We can reduce the mass flow rate. The mass flow rate is a large component of the generation of noise through a pressure reduction device. In general, limiting the valve outlet's Mach number to between 0.4 for continuous operation and 0.5 for intermittently operated systems results in low levels of acoustic energy. We can also develop multi-stage pressure drops. By reducing the pressure of a system over multiple stages, we generally find a lower total sound power level than that of a single stage pressure drop. This multi-stage pressure drop system can also allow for the attenuation of sound between stages. There's also the option to change the valve trim. Some valves are designed to use multi-stage pressure drops within the valve itself, which again will reduce the sound power level. Although the effectiveness and viability of fitting low noise trims should be confirmed with valve manufacturers. Another option is to change the line length in critical locations. AIV typically causes failures at welds, and by increasing the line length between the AIV source and the nearest weld, we can allow for the further attenuation of the sound. Typically, a reduction of 3 decibels can be expected per 50 times the pipe's inner diameter. Then lastly, there's the option of acoustic silencers or sound attenuators. These do what they say, they reduce the levels of sound. However, their use is not generally recommended due to their success rate and limited durability when subjected to the high frequencies of acoustic energy. To make the pipework itself more robust against AIV, we can do multiple things. We can increase the pipe wall thickness. This in turn reduces the high frequency dynamic stress levels and increases the breathing modes of the pipe. A full wrap around reinforcement will do the same and can be used locally around fatigue sensitive locations such as welds to help make the area more robust. Another option is to simply remove or move circumferential discontinuities. Removing discontinuities, such as small bore connections, will improve the system response, since these are often the main fatigue-sensitive locations. Alternatively, using an axisymmetric discontinuity, such as a full wrap reinforcement, improves the response. Moving these discontinuities further downstream also allows the attenuation of noise. The use of circumferential stiffeners can also be performed, where the stiffener rings increase the flexural natural frequencies of the pipework. keeping in mind that these are the modes excited by acoustically induced vibrations. The increase in natural frequency lowers the dynamic stress levels, and the locations of these stiffener rings can be focused around critical locations, although they should be checked by detailed analysis such as FEA. Lastly, the change of connection types can be done, as forged or extruded tees are generally more robust against fatigue than welderlets or welded tees. To mitigate against the source of flow-induced vibrations, FIV, we can reduce the flow velocity, as flow velocity is one of the largest components of turbulence and thus FIV. This reduction can reduce the excitation energy. This can be done by increasing the pipe diameter, running a second pipe in parallel, or by changing operating conditions. Flow smoothing can also be introduced into the line. Smoother flow paths lead to lower turbulence levels. This can be done by increasing the internal radii of T's, increasing the radii of elbows, using flow straighteners, or by increasing the distance between flow discontinuities, thus returning the flow to a uniform regime. If the FIV source is from a valve, then changing the valve type to one with high flow recovery factors can help to maintain the flow regime, resulting in minimal turbulence. High recovery factor valves are often identifiable by a relatively clear and straight flow path. Thus, rotary valves such as butterfly and ball valves are typically good. The alteration of the valve trim can also help to improve the flow recovery. To mitigate the Pipework's response against FIV, we can stiffen the supporting via adding, altering, or tightening the supports. This increases the natural frequency, and as the high frequency excitations are often less energetic than the low frequency, we reduce the impact of the constructive vibrations from the broadband source. Do be careful in the use of this mitigation measure that to not introduce high stresses due to thermal expansion, or to induce resonance with other tonal vibrations present within the system. The addition of viscous dampers allows for quasi-static movement whilst dampening vibrations. However, these dampeners are often ineffective at frequencies over 30 Hz or for narrowband excitation. Shock arresters, absorbers, or snubbers can also be introduced. These can help provide resistance to vibrational movement. We can also use composite pipework wraps, which help to increase the stiffness of the line, thus helping to provide some damping to the pipework's response. And lastly, increasing the pipe wall thickness increases the structural inertia of the pipe, therefore decreasing dynamic stress levels at a given level of excitation. When mitigating against PFIE, periodic flow induced excitations, we can change the operational fluid velocity, which in turn will alter the frequency of the discrete excitation, and thus, if removed by approximately 20% of the natural frequency, will become less problematic. Another option is to change the line length. This detunes the acoustic standing waves, although this won't eliminate the instabilities, only alter the pipework's resonant response. Lastly, to mitigate the pipework response versus PFIE, we require to detune the pipework, as PFIE is a discrete vibrational source. Changing the mass or stiffness will prevent resonance from occurring, although changing the piping's natural frequency should be done with care, so as to ensure that the moved natural frequencies do not coincide with other discrete excitations.